Maybe we can start. Welcome to the live session for the week 12 for the course Semiconductor Device Modeling and Simulation, which is taught by Professor Vivek Dikshit from IIT Kharagpur. And I am Anant Singhal, a PhD student from IIT Jodhpur. And today is the last week of this particular course, session wise. So, today we'll be covering the last part of this course, that is some of the commercial tools, like some of the explanation of the very basic explanation of the commercial tool that we have for the device design and simulations. And yeah, so there will be one extra lecture for the summary tomorrow, that is from 6 to 7 p.m. So I encourage you all to please attend the lecture because I'll be giving the summary of all the weeks and all the important questions that might help you in your examinations and all. So yeah, as you can see, so this is the course outline. So we have come to the last week of this course. So if you remember, we started with very basics on how what is a material, why silicon, and what are these different devices that we use in the week one. Then we went towards the physics of those devices, how the electron travels from here and there, what is the speed of the electron, that is the mobility of electron, what is the statistics that is being followed, like the Fermi Dirac and all. And then we learned about some of the devices such as the PN junction, what is PN junction, what is BJT, and what is this field effect transistor such as MOSFET or MOSCAP, for a easier note. And then after covering all the devices, we went towards these models. So I hope you now are able to understand the basic flow of this particular course. Uh, so what we did is we tried to understand about the material first. Then we, using those material, we try to make a device and try to understand the physics of the device, how the current is coming on applying the voltage. And then because there is a huge complexity, so we have made certain models to mimic the actual behavior of the device so that it can basically help in saving a lot of cost before the fabrication. Because if we can have certain models which can simulate the device or prior to the fabrication, it will be very helpful for the designers as well as the circuit implementers. So yeah, so we as compact models are the bridge in between these two. So we help the people uh, basically before the fabrication to have certain idea about what could be the how we can save the cost of the fabrication, or how could the device may behave because of the certain different models or the different behaviors that we have. So yeah, we'll be seeing like very basic of the Centaurus ticket. So I'll maybe going through like what is the flow in the ticket also. This is will be the same flow that I told you in the software also. So yeah, I'll be telling you the basic of that. And then yeah, these models are inherent in TCAD. So these drift diffusion models. So all those equations that we derived, if you remember the continuity and all, so they are inbuilt in the TCAD software, the Schrodinger-Poisson equation. And also, what happens that for any device that we will be designing inside the software, it just solves the all these equation at all the points that that we'll be able to define. So this is how the software also works. So yeah, let's see what is this TCAD. So TCAD, it is nothing but the technology, computer aided design. So we are just using some technology to basically helping in designing the devices and simulating them to see the IV behavior or CV behavior of those devices. So so yeah, can you tell why do we need TCAD? I have just explained it a bit, but yeah, it would be great if you can give your point of view. Anyone? No, TCAD is not okay. Yeah, okay, that is a fair point, but TCAD is not simplifying the model. So models are there, so very complex models. So okay, so you need to understand that there are very complex models that are there. So what we are doing is using the TCAD, we are even implementing those complex models and designing any device. So TCAD is just helping you to simulate and design the device so that before you actually fabricate the device, you should have a good idea about how the device will be behaving actually when you have those devices. So that is why we want TCAD beforehand. Yeah, yeah. So yeah, yeah. Yeah, kind of. So what you can do in the simulation, you can directly change the, let's say, the length of the MOSFET or the length of the channel of the MOSFET to various different geometries. So you'll get the idea if the length will get shortened out, what short channel effect is dominating and all. So that is why these simulations help. And even after these also, we have the compact models to mimic this device design. So as I told you, there are several compact models. Those equations are implemented in the SPICE simulators also to mimic the same IV. So what I'm trying to say, let's say you have an actual device. Let's say you have a fabricated MOSFET, for example. So this is something like this. So SiO2 gate and all. Oh, sorry, this is drain. This is body. So let's say you actually fabricate a MOSFET and you get a certain IV. So let's say this is ID. I'm not denoting the y-axis now. So if it is looking like this, what is the x-axis? If it looks like this, is it VG or VD? Okay, so this is IDVG because what we have is we have a threshold voltage. Before this, the device is turned off, and after that, the device turns on. The IDVD looks something like this, if you remember. So yeah, let's say you have fabricated a device, let's say at certain VG, maybe at 0.05 volts, which is the linear scale. So let's say, yeah, so this is the IDVG, let's say IDVD for, let's say, VG equals to 0.05, and this is the VD is equals to 0.05. So this is nothing but IDVG in the linear region, right? Because we have a very low drain voltage. Similarly, now this is, let's say, VG is also 0.05. So this is the IDVD for that. So now you have this particular device behavior. Now what you want to do is, let's say you want to mimic this behavior. Like your simulation should also give the same current. So what you can do is you can tune few parameters such as mobility. So let's say you made the same device in the simulation now. So this is the fabricated one. You designed the same in the simulation. I'll tell you how to do that. And that device is giving something like this. So what you can do is you can use the tuning parameters such as I think now you have the good knowledge. So if you increase the mobility, the current will increase, right? Because more the mobility, more will be the current. Or in fact, if you yeah, so there are work functions parameters such as the flat band voltage. So if you, let's say, if you increase the mobility, this whole current will go up, right? So what you do is you try to match this with a actual real application device. So let's say you have able to match this. So now you can use those simulation to have the more detailed analysis of this particular device. You can apply different biases and see what is the different behavior. So if you apply more VD, so it will go up like that, right? So let's say this is VD equals to VDD like that. So you can do a very detailed analysis or the more physical analysis. You can understand the physics of the device. So, for instance, we did, if you remember, we what we did is we that short channel effects. I guess we have covered through the course, or even not the short channel, but we know that there is a thing called velocity saturation, right? So the velocity saturates because of this. This current saturates, right? So you can have this particular, but due to the channel length modulation, we have this factor 1 plus lambda VDS. Because of that, it not exactly remains straight, but it just changes to have it does have a certain ID change. So you can see those parameters inside the ticket and see what is the parameter that is being needed, and you can just fit the fabricated data with the ticket data. So I mean, this is the very basic. I'll tell you how it exactly works. So yeah, so this is what is TCAD. So this is how this is how a designing of a device looks like. So this is some complex device. So just ignore that. So this is a nano sheet. But if you want to design a MOSFET, it will look exactly like this. This is N plus. This is P substrate, and then we'll define some font text and all. So I'll tell you how. So this is gate, source, drain, and this is body. So as I said, TCAD stands for the technology computer aided designs, and we are using the simulation to design a device and mimicking the foundry process or the fabricated device. Foundry is where the device fabrication takes place. Then what we are doing, we are solving the physical based equations the partial differential equations, such as the Poisson or the Schrodinger equation that we studied in the last lecture and the last to last lecture, to predict the device electrical behavior. So you see here IDVG. So this is on the linear scale and this is on the log scale. So if you see the ID on the linear scale is giving some trends. So so yeah, I mean these some in-depth analysis has been done by Ohm also, which is the other T of this course. So he might be telling you about the process parameters also in his slides. But yeah, I'm giving you the very basic idea about the TCAD. So what we can do is we can optimize the process for new technology. So what we can do some length scaling, or we can do some parameter scaling to see what is the behavior of the device without actually fabricating all those different lengths of the device. That will what will it will do, it will save you, or it will cut down the time as well as the cost, and it will enable the low cost exploration and experimentation with the device. So I hope these all points are clear, because these are very straightforward now, and this is why we are using the commercial tools to just mimic the foundry data. So this is the flow that we have. So there is a panel called as Centaurus process. So there are two different things. So either of them you can use. So either it is Centaurus structure editor, which is also called as SDE. So in this, what you do is you have a GUI. So I don't know. Yeah. So maybe I can show you. So this is the Centaurus device structure editor. Yeah. So in this, what you can do is you can make out. You can. Okay. Wait. Yeah. So this is how a Centaurus structure editor looks like. So you see here there is some device that has been made. So this must be some kind of material. So this is mostly silicon. Then this is some kind of material. This is again silicon. Then we have applied certain contacts and all. And this is the gate part. This should be source and drain. So we'll just add some source and drain later and something like that. So this is how the SDE, the Centaurus device editor, looks like, and this is a GUI part using which you can make whatever you want. So for instance, what we have done to make this device is, so we have first made maybe a shorter box. So this is, let's say we have named the P type of substrate. Then we have deposited some oxide. So this might be the SiO2. So different materials have different colors in the GUI. So this is the first thing that we need to do. So this is like making a device. So actually you can define the length. So this may be, let's say 10, not 10, but let's say 90 nanometer or something like that. We can also define the width of the device. So this is a 2D device, that is, it is not a 3D device. The width backend is itself not taken care of. So it is by default 1 micrometer, but yeah, that is not the point. So it is, let's say, a 2D device, you make it like a paper, and then you can simulate it. So this is the first step, that is the Centaurus device or structure editor. Similarly, you have a complex thing also, which is known as Centaurus process. So this can also cover the different length scaling and all. And yeah, this is more of the complex part. So I'll tell you the basic only. So this is the first thing, that is we make that actual device, or we try to mimic that actual device using the Centaurus structure editor. Then there is a meshing. So there is this meshing means. So what you are doing is, now you are, as you have made this device, maybe I can make it somewhere. So I'll explain later. Maybe I can tell you very basically. So what do you want is, you want to know the behavior of the electrons in the channel, right? So what you do is you just divide the device into a lot of parts, and every intersection in you what you do is you just solve the Schrodinger Poisson equation. So that will be able to tell you the charge density, the electron density and all, right? So if just dividing this part or the device into small parts is known as the meshing of the device. So smaller the meshing of the device or finer the meshing of the device, you will get more good characteristics, because you are solving it at the more parts. But if you take a very long, or let's say wide mesh, something like this, so let's say you have only taken these 3 points, so you will only be able to get the behavior like this. So it is not very accurate. So you need to have a trade-off between the meshing also. So I'll tell you what is a trade-off later, but I'm just giving you the basic idea what is a mesh. So this is what the second step is. Once you made the device and you have fixed all the mesh points, so now at every mesh points, what do you want? You want that all the physical equation gets solved. So that part is covered in the Centaurus device. So this is a different thing. So this is S device. So this was SDE. So meshing is inside this only, there is no separate file. So this is now this edge device. So in this, all the physics, all the parameters, materials covers comes under this. Then now once you have simulated, let's say all the physical models, you want to see how it looks like, right? So to see all the IV, CV behaviors, there is this thing called S visual. So you can see all the IVs. So you can plot IV and all using the S visual. So this is the basic flow. And if you use S process, there is this inspect. So inspect also is a some advanced thing that can help you solve even the, so as I can say, so let's say I have IV, so it is like this, right? So inspect, what we can do is we can also extract certain parameters. So let's say this is IV, you want to extract what is the exact VT. So this inspect thing can do that. As visual will only show you the data, it will not extract anything. But this inspect has some more capabilities. But the basic flow is we design the device in the SD, then we do the meshing of the device. Once we do the meshing, we run all the equations using S device, and then using S visual, we see all the trends. Does it make sense? Yes. Yeah. So yeah, it is already there. Right? That is what I'm saying. So as I told you that mathematically all the equations are there. So for example, if you remember, there is this continuity equation, or let's say even a simpler one, let's say the Poisson equation. So we have d2v by dx2 equals to minus rho by epsilon. So using this, we calculate, if you remember, using this, we calculate, first of all, the charge density, how it looks like. Oh, okay, so let me take a very easier case. So we did this PN junction diode. In this PN junction diode, we know that for n side, it is something like this. So this is the rho. Then we do the integration of that to get the electric field, right? This is d by dx also. So electric field, if you remember, it looks something like this. And then we do one more integration to get the potential. So it looks something like this, if you remember. So this is the second order polynomials and something like that. So all these equations are getting solved, right? What we are doing is we are trying to solve this. So these equations are already fed into the ticket simulator. So I'll tell you where are these equations and how they are being solved. So don't worry about that. So yeah, so let's start with the flow now. Yes. So inspect, as I said, it gives you some more complex, some more additional facilities of extracting the data. So let's say you have the single IV, right? So S visual is only helping you in showing the IV. But let's say if you want to have a VT extraction, so this inspect thing can also do that. So you can have maybe SS extraction. So the log scale, it looks something like this. So you can extract the SS using some method. You can extract the VT using some method. So inspect allows you to do that. But as visual is only to just view the data. Yeah. So once we have generated the structure or made the device design, as I said, what we do is we mesh the device. So you see these black lines are the meshing, right? So device is basically discretized into meshing or grid lines. So this is what is meshing is, and all the physical equation like the Poisson, the drift, diffusion, the continuity, all are getting solved at each of these points, right? I hope you understand. So these points, I'm trying to I'm trying to make a dot dot in the device. So if you can see, so at each of the points, this Poisson and Schrodinger equation or the drift diffusion equation will get solved to give you uh, to give you the exact electron behavior, that is to calculate the electron density, charge density, etc. So once you do the meshing, you went towards the equation, right? So one thing I told you before, that we should have a good control over the meshing. So if you do a very wide meshing, so let's say you have made less points, so that is called as coarse meshing or low points, less number of points, not low, less points. So what can happen is in the behavior. So let's say this is a ticket. So this is a doping concentration versus the position of the device. So you see there is some discontinuity. You have only these points. It is not very smooth. But for the same device, if you take large number of points, as you can see, this there are more points here because you can't even see. There are so many points in the green point. So this is called as fine meshing. That is more points. So once you hmm, So course, yeah, you should make fine mesh, but you should not make very fine mesh because that will take more simulation time. I hope you understand that at each and every point the equation is getting solved. So more, yeah. So if you make very high meshing, the equation will be solved in a lot of time. Like it will take a lot of time to get the equation solved. But you should have a trade-off between the coarse and fine. So you should be somewhere in between. That is why what the point is of this particular slide. Yeah. So once now you have meshed, you have done the meshing of the device. Now comes the physical part, that is the solve. So there are few major sections in the S device command file. So there is this command file that is you can, there is something called sdevice.cmd in which this is all the explanation. So I'll tell you what is this all. So the major section, so first of all, it includes the description of the input-output files, the definition of the electrodes. So for example, I have a example file of this PN junction diode. So we have a file, the input files are the grid. So the grid file has the extension of .tdr, right? The meshing point that the mesh file that we have just made in the above, so it has a section of TDR. So it just takes the input file and it generates all these output file. First of all, it will generate what we want is we want the current, let's say. So it will generate a current plot using the .plt extension. Similarly, it will generate all the plot or the output. You need to remember the output is saved in the .log file. That is a .log file. So .log file involves or includes all the current data that is after the. So let's say this is the PN junction. Here I will be applying some electrodes, right? Here let's say I have applied a P electrode. Here I applied a N electrode, right? So once you apply a certain VP, let's say it starts to increase from 0 to some value. So you have a certain current, right? So this current will be solved in the saved in the log file, and this input you are giving here. By meshing at each and every point you are giving the input. So here is the electrode section. So you have defined this P electrode, let's say as anode, the N electrode as cathode. And you are given the voltage value at 0 and 0 for both the sides. So you can give whatever you want. I'm just giving you a very basic example. So this is the first part of the file in which all the electrodes are getting defined and there is a description of the inputs and output file. Then we go towards the physics, as I said. So there are now several physical models. You were saying that where are these equations are getting solved. So now this is the second part. So in the same file that is the sdevice.cmd, there is a section known as physics. So in this physics section, there are different models that are there. So there are mobility models which are doping dependence, high field saturation, E normal. So these are all the models. So E normal means normal electric field model. The high field saturation means the velocity saturation model. I hope you remember that we have those velocity saturation models in which VD equals to mu is not applicable for each and everywhere, but it is something called as some 1 plus mu upon mu critical, something like that. So all these models are written inside this mobility section. So you see, just by writing this, all the models will be solved. So there is a file in which all these equations are already there. Then there are recombination model. We did study about the SRH recombination, the Auger recombination, the avalanche recombination. You remember avalanche is because of the impact ionization for the device. Then Auger is due to through excitons. Yeah, yeah, multiple carriers. Yeah, so yeah, so SRH. Sorry. Yeah. So all these models are already fed inside these files. So you just need to name the model in the command file. So first, what we did is we have the input and outputs that we want. We defined the electrodes where we want to apply the voltage. Then we applied all the physical model, right? So now what we'll do is we'll now give the voltage a sweep, right? We'll start to increase the voltage and see what is the current. So that is the last part. That is the solving part. So there is a solve part in this particular file in which we do the sum of the iterations. So you don't need to go inside, I mean, too much. But what we are doing at every point, we are solving the Poisson equation for each of the hole and each of the electron. So for the, let's say for maybe N MOSFET, what is the majority carriers in the channel? That is the N, right? So we'll be more interested towards the flow, see the flow of the electrons, how it is happening. And now this is the quasi-stationary sections in which the voltage ramps. So here you see the goal of this is to make the anode voltage up to 0.8. So initially, if you remember, the voltage was 0, right? Now what we want is for each and every point, let's say 0.1, 0.2, 0.8 for, I mean, very basic example. So we want to see what is the current. So it will solve at 0.1, it will go to 0.2, it will go to 3, it will go to 4, and like that it will go to 0.8. So this particular quasi-stationary section does that. Here you see the initial step is this. I mean, there are several different kinds of thing in the file, but yeah, the basic thing that it is doing is it is just taking the anode voltage from 0 to 0.8. You can define whatever voltage you want here. If you write 0.5, it will go till 0.5. So this is how it works. So we define the input and outputs, we define the electrodes, we define whatever the physics that we want, and then we just solve those equations. I hope it is clear. So yeah, this is the complete kind of flow. So this is a MOSFET that we designed. We did the meshing. The black part is the meshing. So we did more meshing in the channel because that is what we are more interested in. How what is the channel current? Then we have this TDR file out of the meshing. Then edge device, what it do is it takes all the parameters from the, I mean, so every every material has some different parameters. Like silicon has something different, SiO2 has something different. For example, the epsilon of Si is 11.7, SiO2 is 3.9. So all of these different materials have different parameters. So there is a parameter file which has extension of .par. There is a CMD file that we were talking about. So using this, we have this Centaurus device, that is S device, which will solve all the equation as I just said. So this part is solving the equation and giving the output as the plots of current, etc. Right? So this is the current plot. You see, we have been able to have the IDVG plot. So this is a complete flow. I hope it is fine. Sorry. Yeah. Yeah. So yeah, it is a long process. Even the simulation takes a lot of time to generate this IV. It will take a lot of time to go from. So that is, I mean, if you are saving up on actually making the device, you need to have some good analysis of the device. So yeah, you need to have some computational cost over it because the actual fabrication is way more costlier. So yeah, this is, I mean, this is the least you can do to have the analysis. So this is a single device. Similarly, you can do some length scaling of this device. You can make 10 different devices of different 10 lengths and it will give you the 10 IVs. So that will help you in understanding what is exactly happening. Like the VT should increase or decrease on decreasing the length, or the VT should increase. There are several short channel effects that you can implement, such as roll off. So, if you remember, there is a thing called VTH roll off, that is a threshold voltage roll off, in which what happens is if we go to very short channels, the threshold voltage suddenly starts to decrease. So you can check that, or if you go to a very long channel, basically the threshold voltage does not change; it saturates. So the VT versus land trends look something like this. So yeah, I mean this is all the basic. So this is all you can do using the Ticket software. I guess in the tutorials or the exact lectures they have also covered the Silvaco software. So there are two versions of this Ticket. One is Silvaco Ticket and one is Synopsys Centaurus Ticket. So all the screenshots that I have shown you is from this particular software, that is the Synopsys Centaurus Ticket. This Silvaco one is maybe open source or some version is available for free. So you can also try to download, and I mean maybe the videos has all the links and all to have the exposure towards the actual software. But this Synopsys you don't have a free license, so yeah, it is quite expensive. So you can try out Silvaco. So that is also similar. So there are files that you have in Silvaco. You can design the device, then go towards the solving the equations and get the IVs and all. Yeah. So yeah, let's see some of the problems now, which are very quite straightforward because I mean these are the problems related to the tools. So yeah, maybe side by side you can let me know the answer when you can, and yeah, we can go towards the problems quickly. Yeah. Yes. So tomorrow 6 to 7 there will be a session for summarizing the whole course. Yeah. What class? Yeah, but yeah, I mean, I cannot shift that now, but that will be only like 50 minutes class. So 6 to 7, if you can manage, you can. Otherwise you can see that later in the recording and all. Yeah, and if you have any doubts regarding some particular week, you can ask that in the tomorrow's class. So, I mean, the basic idea is to just give you the summary of all the classes that we already have. To, I mean, yeah, 6 to 7. Hmm. Yes, yes. I mean, very quickly, I will go through all the 12 weeks PPT and let you know that which part I think is important and yeah, what you should focus on more, something like that. So I'll go through like this is 1 week PPT. Similarly, I'll go towards all the 11 PPTs and try to quickly wrap up to see in 50 minutes if we can do that. That this should be a very important thing that you should study for the exams. Yeah. So yeah, just quickly let me know the answer to this particular problem and then we can move ahead. Okay, let me give you a hint. Yeah, here it is written. So you can take the reference from here. Sorry. Yeah. So these are all the files. So yeah, log file is exactly for this. Yeah, for storing the output. So maybe I can see what are the option. Yeah, so log file is it is not specifying material properties because it is .par file. Yeah, to store the IV is correct. It will not create the structure. It will not eliminate the mesh. So option B is the correct answer. Sorry, .par. I showed you there here. You see here, here. Yeah, parameter. Yeah. So now let's see. So okay, so there are few commands in Tcad that you can learn later, but yeah, this there is this eliminate command that is basically help you to eliminate the sum of the mesh points. If the meshing is very fine, you can eliminate few mesh points using the eliminate command. So option A is the correct answer to this particular problem. It does not eliminate the electrodes, it does not eliminate any material, and it does not eliminate any region. So option A is the correct answer. Yeah. Okay, so yeah, you can try out. So yeah, so there are few keywords now in TCAD. So once you are designing the device, there is some kind of script that is being generated whenever you are designing a device. So in that script, you need to see now how does exactly the script work. So in the SDE, you are designing the device, right? So this is getting transferred into a script, which is known as SDE file, in which you are defining what is the doping of this region. You are defining all the regions that this box is silicon, the position of this is this XY coordinates and all. So that file is SD file, and then the screenshot which I showed you was H device files. So in the SD files there is this concentration, so it can be shortened to concentration as, but the thing is this concentration or this CONC should not match with some other or some other variable. So it's okay if you don't use a full name, but if it distinguishes from the other commands. I hope it is clear. So both of these statements are correct. Yeah, and the reason, yeah. So option A is the correct answer to this. Yeah, let's move forward. So what is a devolved behavior? So yeah, there is a Silvaco and then there is Centaurus. So in Centaurus, so I hope there is a lecture in which I covered the omega and Schottky contacts. So from that only we came to know that why do we even dope the source and drain to very high, because the metal contact have a very high doping, right? So we need to dope them high so that there is comparable. So if it is not comparable, then there will be a Schottky contact, right? So if you just if there is, let's say, a p type substrate, and if you just make the contact directly, so this can be Schottky because of the very high metal work function difference, metal semiconductor work function difference. But if you make the doping higher, so it will become ohmic. So the default behavior of contacts is ohmic only. Yeah. So let's move ahead. Okay, so then we have logical parameters can be set to false. Okay, so let's say if you want to have any value which is, let's say, 1, for example. So if you want to negate this value, you can just write or you can set to false by adding a cap symbol before them. So you just have a cap symbol like that, and it will get negated. So if it was 1, it will get to -1. So this is correct. Then the con mob is a concentration mobility model. Yeah, so it accounts for the concentration. So this is also correct. And then Athena. So yeah, this is a framework in which you can make all the programs that are being stored there into a process simulation tool. So this all the statements are correct. So option C is the correct answer to this. Yeah. So yeah, in the TCAD, so what you did is you designed a device. Now what you exactly want. So if you see in the some of the lectures, what we are doing is we are making a MOSFET and then we are applying some VG. We are trying to add some of the resistance and we want to now see what is the circuit behavior like. So this is the device level only. Now you want the circuit behavior also, right? So to do that, yeah, yeah. So for transient analysis, or let's say if you want to do AC analysis or DC analysis, there are a lot of analysis, but you can do that also in TCAD. So you can do this particular simulation is called as mixed mode simulations. So there is a way you can define all these registers and all the additional voltage sources in the again the edge device file, and you can do the mixed mode simulations also. So for AC simulation, the statement is dot AC. For transient, it is dot tran. The DC is dot DC. Yeah, these are the three main statements. So here the dot tran is for the transient analysis. I hope it is fine. So let's move ahead. Yeah, so this is more of a theoretical question. So it says the diagram illustrates the electric field distribution in a MOS structure under a specific gate voltage. Given that the flat band voltage is 0, the threshold voltage is given by. So this is a problem. If you remember the particular formula, the whole flow that I have done in the MOS cap, you will be able to solve it. So maybe you can take 5 minutes and let me know what is the answer that you have reached to. anything. So let me give you an idea. So if you remember, the VT formula was nothing but the Q depletion by C ox plus 2 5F. So here the VAB is 0, so this part will not be there. So the VT will be Q depletion by C ox plus 2 5F. So now what we need to see is what are all the values that have been given to us. So yeah, okay. So if you remember the Q depletion, the formula was 2QNA epsilon S and then 2 5F, right? So that was psi S. And then for 5F, we know it is VT ln Na over Ni. So in both these formulas, what is the thing that you don't know? So you know what is Q, you know what is phi S, you know what is, oh sorry, psi S you don't know. And this psi S is this. In this you know VT, you know Ni. So the only thing that you need to know from the diagram is the doping. If you can get Na, you will be able to solve VT, right? So how can you get the doping? By seeing this. So you see that there is this electric field change, right? So there is a material here that is being, so if you remember, there is in the p-n junction diode also, the electric field looks something like this. So wherever there is this peak, this is called as Emax, right? And if you remember, the formula for Emax was, it was nothing but QNA into width of that particular region by epsilon s. So you know the width is this much, which is, let me remove this, yeah. So the width is in microns, that is 0.8 minus 0.6, that is 0.6 micrometer. So now you know the width, you know the Q, you know the epsilon s. Emax, you can see what is the maximum electric field. It is nothing but 10 kilovolt per centimeter, right? So this is E, not F. So now what you know is this is 10 kilovolt per centimeter. This is Q is 1.6, 10 minus 19. Na you want to calculate, this is 6.6 micron. So let me write in centimeter only. And then epsilon s is nothing but 11.7 into 8.85 into 10 raised to power minus 14. So basically this will give you all the doping, right? So I mean just in terms of order, so this will be minus 23 minus 14. So it will be minus 9. Okay. So it will be 10 into 11.7 multiplied by 8.85 multiplied by 9 raised to power 19. So it is kilovolt, so it will be 10 raised to power 4 overall. And then it is divided by this 1.6 by 0.6. Yeah, so this will give you the sum value of the n, which is around 10 raised to power 20 or something like that, which is quite high. I hope you understand what I'm trying to say. Is it clear? Yeah, so once you can find the Na, you just need to put it here. You will get the phi f. Sorry, there's some noise. Yeah, it is fine now. So once you get the phi f, you will get this QDP. Sorry, once you get the Na, you will get this Q depletion also, and you can just feed it, and everything else is given. So the answer that you will get is, I'll just tell you the answer. You can solve it. You can solve it after the class, and let me know what is the answer tomorrow. So the answer that you should get is around 1.45 volts. Something like that will be the answer. Is it clear the way we need to solve this particular problem? Yeah, yeah, yeah. So you just feed it here, and now you know that for silicon it's 1.15. 10 is per 10. So you will get 5f, which is nothing but, so 5f sin s is 2 5f. So here if you just put 2 5f, you will get the Q depletion, and then 2 5f, you already know Q depletion, you know, you will get the VT. Yeah. So let's try to do this now. So it says consider a n-type semiconductor of length L in equilibrium. So that is the main hint of this problem. Given the doping profile is this equation for charge densities. So you need to find that out the row. The equation for row, not the row. And again the hint is neglect the whole concentration. So P is very, very, very less than N. So this is a very easy question if you can understand that what do we need to solve in equilibrium. So the hint is that J total in equilibrium is always zero. So this is the hint. Maybe you can give 2 3 minutes and then I'll also solve it. Or one more hint is J total is nothing but J diffusion plus drift, and you need to neglect the whole part. And if this is equals to zero, you need to do that. Yeah. Just let me know if you can solve it, and then I'll also solve it. Any solution or anything? Okay, fine. So let me solve it. So as I said, first of all, this is an N type of semiconductor. So basically there will be Jn drift plus Jn diffusion is equals to zero, because we are neglecting the P side. It is already given in the problem. So what is the current density for the drift part? Can you tell me quickly? It is right, NQ mu and E, right? Plus the diffusion part is nothing but Q dn over dx. This is equals to zero, right? Any doubts in this? And n is already given in the problem, which is this. So you just need to put it. So let me know it is small n. So it is n naught exponential of minus x square by L square. So let's put it here. So it is n naught exponential minus x square by L square q mu n e plus q dn, the differentiation of this. So what will be the differentiation of this? N naught will be constant, then there will be minus 1 by L square, then there will be exponential of minus x by L square, then there will be 2x, right? This is equals to 0. So since all the common terms will go away because they are equals to zero, so what all will go away? Let me just use some other pen. So n naught will go away, exponential will go away. What else? Q will go away, right? So it is like mu n e plus dn by L square, sorry, not plus, minus dn by L square into 2x is equals to 0, right? So now what we can do is we can calculate E from here, which is E is this side it will go, so dn into 2x over L square multiplied by mu n. So if you remember Einstein relation, dn is nothing but mu n into vt, right? Yeah, so mu n will get also cancelled out, so the electric field will come out to be, so mu n will cancel out, mu vt will remain, so 2x into vt over L square. Any doubt in this? Clear? So now you know what is electric field. You need to find out the charge density. What will you do? Which, yeah, sorry, charge density is what? What is this formula? I don't understand. Okay, just let me know what is Poisson. What is Poisson equation? Can you tell what is Poisson equation? So what it is? Right, this is a Poisson equation. d2v by dx2 is minus rho by epsilon, right? And what do you think? So the differentiation of electric field is minus d, right? Because v is d over dx, right? Sorry, the other way. The electric field is dv over dx. This is the Poisson equation, right? So basically, dE over dx is rho by epsilon. You know the E. You need to find the rho. Sorry, 4 Vt square. What did you do? What you need to do is rho you need to calculate. So it is epsilon into dE by dx, right? We just need to differentiate this. Yeah. Yeah, so if this is maybe charge density, then it will be multiplied by Q, but yeah, this is the answer. Where? Why there will be a minus sign? The differentiation of x is 1. So that is the only part that will change. Yeah, so this is the answer. Is it clear? You can see the recording later if it is not. Let's come to the next problem. So it says the energy band diagram of the MOS capacitor is shown and the thickness of oxide is this. Then you need to answer the following questions. Assuming Ni is 10 raised to power 10. So what is the whole concentration at the surface? So yeah, let's start with one by one. So yeah, what is the whole concentration at the surface it is asking. At the surface you see x is equals to 0. And the whole concentration, that is a minority carrier concentration, is nothing but 10 is per exponential of x, if you remember. So this is 10 raised to power exponential, at the surface it is 0. So it will be nothing but equals to Ni only, that is 10 is per 10 per centimeter cube. Okay. What is the surface potential? So what is surface potential? You know what is the surface potential? The difference between surface potential is a difference between what, which energy levels? Yeah, so where, but at the surface, at the where? No, no. So surface potential, yeah, at the surface, but it is equals to the difference at the surface bulk minus EF bulk. So basically, this particular change in the EI from at the surface is the surface potential, and it is given as 0.6 electron volts. So the potential will, if I say, it will be 0.6 volts, right? Okay, so the third problem is what is the gate voltage applied? This is a, yeah, how Fermi level is, yeah, exactly, yeah. So that is the correct answer. So since the Fermi level of both semiconductor and metal are at the same line, so that means that there is no gate voltage applied. Once I apply the gate voltage, the Fermi level will either go up or down. Yeah, because of the metal work function semiconductor difference. Sorry, metal semiconductor work function difference. So the Vg will be 0, the surface potential will be zero point 0.6, and the whole concentration will be 10 raised to 10. Make sense? Okay, so let's cover few TCAT problems now quickly, and then maybe we can wrap up. So Nilesh, maybe you can see the video for the TCAT part. I've just already covered it, so you can see the video later. So yeah. So first problem is, so okay, I'm just asking. Let me know the answers quickly if you can. Otherwise, I'll just tell you. So the first problem is, which tool is primarily used for the device level simulations? So is it S process? I'm just writing the options and saying the problem. S visual, or is it S device, or is it S mesh? Which tool is for the device simulations? Yeah, so S device is the correct answer. That is good. So the next problem is which, okay. So the problem is command to run, sorry, again, command to run the S device simulations. So what is the command to run the S device simulations? I guess I'm not told, so let me tell that. So SDE is the command which is used to run the device editor. This is where the device editor will open. That is this blue window I just showed. Maybe, yeah. Yeah, this will open using the command SDE. Then to simulate the device, the command is SDevice. Wait, I'll write there only. So yeah, for SDevice simulation, the command is SDevice, whatever the file name, and this file is .cmd. Is it fine? And to open the plots, it is svisual. Is it fine? So yeah, it will open a window in which you can do whatever you want. So if you want to plot current on the x-axis, voltage on the x-axis, something like that, this will open that window for you. So now the next question is, which file contains the material and the physical models? Is it .tdr file? Is it .cmd? Is it .par? Is it .mdl? So which file contains the material and physical models? Okay, and TDR is a mesh file. I just told you that the parameter has all the so the materials and the models are in the parameter file. So dot par has material and physical models. Okay. So now the next problem is, what does the sdevice dot par file contain? So I just told you, so I'll just leave that. Okay. Yeah, let me see if I have few more. Okay. So yeah. One more thing I'd like to add is, so as I told you that all these equations are getting solved in the backend, right? So but these equations are not solvable because these are partial differential equations, such as this also. If you do it for a 3D device, which is very complex because each and every point the voltage is changing, it is not very straightforward, right? So these are solved using numerical methods that we covered in maybe one of the lectures. And TCAD uses the Newton-Raphson method. This is what I wanted to tell you. So this is again a numerical technique which is used to compute the differential equations which are not solvable. So Newton-Raphson method is used to solve all the partial or the differential equations. Make sense? Yeah. So again, what is the file extension for the structure input file? Input file, you remember we do the meshing, so what will be the extension out of all these? Yeah. Oh, CMD is only the edge device simulations are happening in CMD. Input we are giving the mesh, right? So it will be .tdr. Yeah, so input file will be .tdr. This file will go inside the CMD. CMD will solve all the equation using the physical models in the pair file, and the output file will be .log. This is what the first question was. Fine? Yeah. So yeah, this is more of it. Let's see. And let me see. So yeah, I mean more on the side, you need to have the clarity on all these only. That how is this, by seeing the diagram, what is like the gate voltage, you can see that it is zero. Similarly, you should have been able to grasp all these, how does the concentration, I mean the question seems to be very weird. If you have just seen the whole subject, you will not be able to guess quickly that what should I do. So you should have that understanding that it is saying that the main two words are in equilibrium. It should strike your mind that in equilibrium we know that J total is zero and total part is nothing but the drift plus diffusion. And it has already given you the n. Where is that? Yeah, it has already given you the n. So this should be related to these equations only. And once you get the electric field, you know that Poisson equation, just differentiate that, will you will get the charge density from that. And differentiating it one more time, you will even get the potential profile also. Right? So these are the few things, I mean, I just wanted to cover, I guess. On the T-gate side, I've already covered a lot in the initial lecture. So yeah, you can see that later also. So is there any doubt? or else we can stop maybe quickly if you have any doubts, because this is the last part of the course. And again, tomorrow we'll be taking the summary class from 6 to 7. And I do hope all of you should attend that, because that will be useful for you for the revision also. I'll try to go through all the 11 or 12 slides quickly and let you know what is the important part in that. Is it fine? Yeah. Okay. Yeah. Then we can stop. Yeah. Good night.